Now let's think about the simple harmonic motion of a particle. So this is like a spring mass system where we have a particle with mass m is attached to a spring and it's making simple harmonic motion. So this is my particle with mass m that is performing simple harmonic motion, and the spring has a spring constant alpha. So I have a particle mass m performing simple harmonic oscillations, simple harmonic motion. Alpha is the spring constant, and if the equilibrium position of this spring is here, this is x equals to 0, then I have deviations from the equilibrium position, the position of the particle given by x, and its momentum given by px. So I can write the energy of this particle as a sum of kinetic and potential energy terms. From the course on classical mechanics, I know that its kinetic energy is px squared divided by 2m, and its potential energy is 1 over 2 alpha x squared, and the total energy is a constant if there is no friction in the system. So the restoring, this is because the restoring force, the spring force by Hooke's law, is given by minus alpha x, where alpha is my spring constant. So let's assume that the system is in equilibrium with a heat reservoir. So I have the system at equilibrium with a heat reservoir at an absolute temperature T. In that case, I'm assuming that this temperature T is high enough so that I can neglect quantum effects. So this is high enough for a classical approximation to hold. So using classical statistical mechanics, the mean energy that includes the quadratic momentum term and quadratic position term, they both have a contribution 1 over 2 kt and 1 over 2 kt. So therefore I find that the mean energy of this particle has to be equal to kt, Boltzmann constant, times its absolute temperature. Okay, so the simple harmonic motion is basically the motion of this particle that is attached to a spring, and I'm assuming this is one-dimensional simple harmonic motion. And if you want to review from classical mechanics, mass times acceleration, the net force acting on this particle is mx double dot is equal to minus alpha x, which has solutions that are oscillatory, and basically we find that x of t is equal to a cosine omega t plus phi, where omega is equal to square root alpha over m. It is 2 pi times the frequency of the oscillations. Omega is angular frequency, phi is the initial phase. So we know this from our physics 101 or 102 introductory physics courses. So the energy has two terms, kinetic and potential, that is due to the translational motion of the center of mass, px squared over 2m, and the potential energy terms comes from the restoring force minus alpha x, that gives me a potential energy 1 over 2 alpha x squared. So remember that this restoring force is a conservative force. It is minus the gradient of the potential energy, and the potential energy is 1 over 2 alpha x squared. So at equilibrium with a heat reservoir at absolute temperature T, my equipartition theorem tells me, due to equipartition of energy, we have 1 over 2 kT contribution to the mean energy of the system for each independent quadratic term in position and momentum. So we have 1 over 2 kT plus 1 over 2 kT. Therefore, the mean energy of this particle will be kT, provided that, this is important, the temperature is high enough for classical approximation. Otherwise, we would have to use quantum mechanical treatment of the simple harmonic oscillator.